You will repeat this motion about 17,000 times today. For the most part, you will do it entirely unconsciously. Every one of those breaths pulls in oxygen to fuel aerobic respiration. That is the chemical process your cells use to produce ATP, the molecular energy source that powers all of their biological functions. Because every single cell requires that energy to survive, drawing air into your chest is the starting gun for a massive, high-stakes logistical operation. The central problem of respiration is a physical limit. Gas enters cells by diffusing from its surroundings. As we see here, that process works over microscopic distances, but oxygen slightly further away dissipates. When scaled to a human body, diffusion fails. An oxygen molecule in your chest cannot drift to a muscle cell in your foot. Because oxygen cannot reach your cells through simple diffusion, the human body uses an engineered transportation network to bridge the gap. Moving that oxygen requires a specialized vehicle, the red blood cell, which is packed with oxygen-binding molecules known as hemoglobin. The raw materials to build this cellular fleet are harvested far from the lungs. Through chemical digestion in the gut, your body breaks down food to extract specific elements, like iron. That iron is transported to your bone marrow cavities, which function as internal manufacturing plants. Their production schedule is regulated by hormones secreted from the kidneys. Following those kidney signals, the bone marrow churns out roughly 2.5 million new red blood cells every single second. To put that manufacturing pace into perspective, your bones produce a number of cells equivalent to the entire human population of Paris every second of your life. Your gut, kidneys, and bones maintain this continuous pace solely to ensure an adequate fleet of vehicles is already waiting when oxygen enters the body. When it is time to load those vehicles, the brainstem sends a signal through the nervous system, commanding the diaphragm and rib muscles to contract and pull air into the lungs. Lungs are often described as two big balloons, but if they were hollow, any air trapped in the center would be too far away from the blood vessels on the edge to diffuse across the membrane. Instead, the lung interior is divided into hundreds of millions of miniature balloon-like projections called alveoli. This structure increases the internal contact area between air and blood, creating roughly 100 square meters of surface area within your chest. The membrane wall separating those alveolar sacs from the blood capillaries is exactly 2 cells thick. By forcing vast volumes of air into this close proximity with the blood supply, the architecture of the lungs allows oxygen to overcome the physical limit of diffusion. Once the oxygen crosses that 2-cell gap and binds to a red blood cell, the final challenge is propelling the loaded vehicle out to the distant cells of the body. The cardiovascular delivery network is so extensive that if you laid a person's blood vessels end to end, they would wrap around the earth several times. Pushing a dense fluid through thousands of miles of microscopic tubing requires a continuous, powerful mechanical pump. That force comes from the heart, a muscular engine that contracts on average 100,000 times per day. This provides the brute force necessary to deliver the oxygen payload to the exact tissues that need it to survive. Delivering just one molecule of oxygen requires the gut, bones, kidneys, brain, lungs, and heart to execute a synchronized performance. If a single part of this biological infrastructure malfunctions, the entire chain collapses. Take a brief moment away from the mechanics and simply focus on your own body in this exact moment. Take one intentional, deep breath in and let it out. Every simple breath is supported by this invisible machinery, continuously coordinating to keep you alive.